Okay, so welcome to this lecture on mini dimensions and outriggers. In the previous lecture we talked about changing dimensions in surrogate keys, and I hope you are now familiar with type 1, type 2, type 3 changes and the role of surrogate keys in handling changing dimensions. So today I'm going to take this topic further, and I'm going to talk about two important concepts in modeling, and these two are mini dimensions and outriggers. And then I'll be introducing changes, type changes from 4 to 7, right? So type 4 is basically adding a mini dimension. So first I'll give you idea about mini dimensions, and then I'll talk about hybrid techniques, which are combinations of the first 4 techniques in right. So so type 5, we'll talk about type 5, which is like mini dimension, and type 1, which is a hybrid of mini dimension and type 1 outrigger. So outriggers also I'll try to explain before that. Then we have type 6, which is add type 1 attributes to type 2 dimensions. So it is a combination of type 1 and type 2, and then we have dual type 1 and type 2 dimensions, that is type 7. So you will see that they allow you to handle different kinds of situations. Mainly these techniques are meant for large dimensions. We call them monster dimensions, which are rapidly changing. So this is the worst possible scenario that you can have, and let us see how we can handle them. So let me just switch off this video so that the entire content is actually visible to you. So this is the outline. So today I'm going to cover all these topics. So you can see. So let me first introduce the monster dimension. So like for example, we have this customer dimension can be very wide, and dozens or hundreds of attributes can be there. Up from dozens to hundreds of attributes are very common. And customer dimensions can be very large, like so they are both like wide and deep, and tens of millions of rows in some warehouses, and sometimes includes prospects as well as actual customers. So prospective customers are also added to this list. And size can lead to performance challenges. One case when performance concerns can trump simplicity. So this is where you have to worry about this performance, and you have to kind of trade off with simplicity. You have to make the model slightly more complex. And the questions that we try to ask is, can we reduce the width of the dimension table? So that is one thing. And can we reduce the number of rows that get added by implementing type 2? Type 2, as you know, when you implement changes using type 2, a new record gets added to the table. So if it's already like 10 million and set 10 million records, and suppose in a year one change happens to every record, so in 1 year your number of records would become 20 million, right? So that is not a very desirable situation, and I am being conservative on the number of changes that can happen, because here we are talking about rapidly changing dimensions. So rapidly changing monster dimensions. So this is the worst scenario, as I told you. So you have multi-million customer dimension present unique challenges that warrant special treatment. And I just explained to you that type 2 SCD, that is slowly changing dimension, is not recommended, because the size of the dimension table would become manifold, right? So we don't recommend that. And also business users often want to track the it is not that we don't want to track the changes. We need to track the changes even if there are multiple changes. For example, insurance companies must update information about their customers and their specific insured automobiles and homes, and they should see what kind of changes have happened at the time, between the time they bought the policy and they are making a claim. So all these things are to be recorded. So there is no way we can say that we don't want to record the changes. Changes have to be recorded. How you record them and how you prevent or how you avoid explosion of rows using type 2, that is the main concern that we are discussing here. And also throws browsing performance and change tracking challenges, right? So browsing performance, basically when you have so many attributes, hundreds of attributes, so browsing also becomes a challenge, and performance definitely becomes a challenge. So what is the solution that we can look for? So the solution that has been proposed is that of a mini dimension. Now first of all, let me explain the name mini dimension, right? So it is called a mini dimension because it has been carved out of a dimension like the customer dimension. So that's what the name mini, and dimension because it acts as a dimension in the overall schema. So if you had the 4 dimension tables before the creation of this mini dimension, you would have, say suppose for 1 dimension I created this mini dimension, so you'll now have 5 dimensions. So any dimension, so whenever we call a table a dimension table, that means that it is going to directly talk to the fact table. So there will be a foreign key from the fact table to this dimension table. So this one technique which can handle both the problems that we posed in the previous slide or the problems that a rapidly changing monster dimension can pose. So it is a solution to all the problems that are there. And what it does is basically it separates out frequently analyzed or frequently changing attributes into a separate dimension called mini dimensions. So basically what we do is we try to identify attributes which are either frequently queried or which are frequently changing, and we put them in a separate dimension and give it a name, a mini dimension. So more on this. So for example, we can separate out package of demographic attributes into a demographic mini dimension. So I remove all the demographic attributes about customers and put them in a separate field, because demographic attributes are one like marital status, age, income levels. They keep on changing. Locality, right? All these things keep on changing. So age, gender, marital status, number of children, income level, etc. They keep on changing, right? So it becomes very difficult to handle them using type 2. So what we do is, like age would have a certain values, right? Gender has only 2 values. Marital status can have 3-4 different values, right? Number of children can also vary from say 0 to 5, 6, whatever. And income levels also can have certain values. I mean, I'm not talking about income correct to the last rupee, or right. So what we are talking about is bands, right? So what we do here is that we create a one row in mini dimension for each unique combination of these attributes. Age also we do a kind of a binning, right? Binning, you understand? So binning is basically a concept where you group together values, right? So we do this for age, and we do this for income, right? So more on this in the next slide. So this is what we do. So what we say is that you can see here we have done bracketing, binning, bracketing, discretization. All these things, all these terms are being used for this kind of process. So I'm saying age is between 20 to 24. It's a male, and income level is less than 20,000. Now there could be another male or another set of persons who are between 20 to 24, and they are all males, and the income level is between 20K to less than 25K, right? Another set would be 25K to 30K, and then we go to another group, and then again male. I mean, it is not by design that there are all males in this particular example. There could be females also. It doesn't matter, right? So let me say that there's a female. Okay. So, and if you look at this, so all kinds of combinations, I put a demographic key. I identify. So if I say demographic key 1, so I understand that it is, I'm talking about customers who are between 20 to 24 years of age, who are males and their income level is less than 20,000. When I say 18, then I'm talking about the age group 25 to 29. I'm talking about females, and their income levels is between 20 to 25K, right? So this is how I do. So now, even if say my age, say if you look at age, okay, say my age is 21, say. Now in 1 year's time this would become 22, okay, and there'll be lots of customers. I'm saying that this is a customer demographic, okay. So there'll be lots of customers whose age would change, right? So say from 21 to 22. Now this change happens, and since I have a bracket here, right, so there is no change that is happening at the individual customer level. If you look at the age column, so I would have recorded for this customer age 20, now it has to be changed to 21, so I would have to do a type 2 change for this, right, and insert a new record. So what happens is that only when the demographic key of a person changes, then only you need to record the change, okay, or make a new record, say implement as a type 2 change, right. So this kind of protects or shields the data warehouse from explosion growth in terms of number of records in the dimension table. So we do discretization, although there is a whenever we discretize, there is a loss of information, because I have lost I only know that the customer is between 20 to 24. I don't know his exact age, right. So mini dimensions, so we call them mini dimensions, so we have to make sure that they don't grow too big, okay. So otherwise the purpose gets defeated. And so many dimensions cannot be itself allowed to grow very large. So 5 demographic attributes, suppose we have 5 demographic attributes, and each can take 10 distinct values. So right, so how many distinct combinations we can have? So you can see that we can have around 1 lakh combinations, right, different combinations. So this is slightly on the higher side, so we don't want the mini dimension to grow as big, right, but depending upon the situation it will have a certain number of records. So now when we create this mini dimension, so what I'll just show it to you. So if this is your fact table and this is your these are your dimensions, so I'm drawing some few dimensions just like that, and suppose this is my customer dimension. So what I have done is I have carved out certain attributes from here, okay, all demographic attributes I have taken. So these are like my demographic attributes, and I have created I'll use some other color. I have taken them out and put them in a mini dimension, and the key for this should be included as a key for this, I mean along with the other keys, right, and there has to be a foreign key from here to here, and there will be no connection between the the customer and the demographic. So the connection will be captured in the fact table, not directly between the customer and the customer dimension and the mini dimension. So this is how it works, right. So that's what is explained in this particular slide. Include foreign keys to both customer anyway is there directly, and mini dimension in fact table. So what we have to do is we have to generate surrogate keys for the mini dimension. So that is one thing you need to do. So generate surrogate key for mini dimension, that is one thing you need to do, and introduce the surrogate key as part of the key in the fact table. So now the advantages of having a mini dimension. So history preserved without space blow up. Fact table captures historical record of attribute values Mini dimension has small number of rows. Number of unique combinations of mini dimension attributes is small, which is a result of the discretization that we have done, right? And this I have already explained this part earlier in the slide. Improves performance for queries that use mini dimension, and at least those queries that don't use the main customer dimension, because mini dimension is small, like the name itself suggests. So if you are constraining the mini dimension, then your query performance would improve compared to when you were all these attributes were there in the main dimension and you were constraining the main dimension. Disadvantages: so nothing comes free, so there will be disadvantages associated with mini dimensions. So fact table width increases because you are introducing a new key. Due to increase in the number of dimension foreign keys, information lost due to discretization. So this is a well understood thing, that when we discretize we lose information. And we have made our schema a little bit more complex by introducing additional tables. So user must remember that and another problem with this is that I should know that which attributes are there in the mini dimension, which I have taken from the which I have extracted from the main dimension and put in the mini dimension, because when I want to constrain the query, right, so I need to know which dimension it is. So that is a cumbersome thing, right? So that is something we need to work on, right? So users must remember which attributes are there in the mini dimension versus main customer dimension. So this is a particular is a problem that it causes. Now, before I move to type 4, type 5, type 6 and type 7 changes, I also want to introduce the concept of outriggers, snowflaking and outriggers. So this is the next subtopic that I'm going to talk about. Okay. So snowflaking is removal of low cardinality columns from dimension tables to separate normalized tables. So snowflaking is basically a kind of a normalization. So you all know that in a dimensional model framework we discouraged normalization, but in some situations we kind of allow normalization, right? So we typically call that outriggers, although outrigger is not necessarily normalization but something similar. So snowflaking not recommended because user presentation becomes difficult, because you are making more and more tables, right? So there is a dimension table, so alright, so you'll carve out something which is linked to this, so that is snowflaking. Okay. So negative impact on browsing performance, because you have to now look at 2 tables instead of 1 when you're looking at this particular dimension, and this would necessitate a join. So whatever attributes are here, so this is my fact table, right? So if I want to constrain on some attributes here, so I'll have to come through this particular table, right, to reach the fact table. So query performance suffers because of the joins, the additional join, and prohibits the use of bitmap indexes, because when you normalize, you are basically taking the low cardinality attributes away. So when you are taking low cardinality attributes away, so basically you are also losing the opportunity to create bitmap indexes on them. And some situations, as I said, permit the use of dimension outriggers, and these outriggers have special characteristics that make them permissible snowflakes. So let me now describe what we mean by snowflakes, what we mean by outriggers. So limited normalization of a large dimension table to save space, and here we try to identify attribute sets with the following properties, that is highly correlated. So these set of attributes are highly correlated and different grain than the dimension, that is the grain is say for the customer dimension it is number of customers, right? So it is at a different grain. And the third important characteristic is that the change in unison, that is if something has to change, a lot of attributes would change together, right? So let me give you an example of an outrigger or a situation where you can use outrigger. So set of data from an external data provider consisting of 150 demographic and socioeconomic attributes regarding the customer's district of residence. So this is not, so that's what I talked about, so the grain, right? So these attributes apply at the district level because it's demographic and socioeconomic attributes of the district, not of the customer. So the grain is quite different, and it is not at the customer level like I mentioned in the previous slide. And data for all customers residing in a particular district is identical. So what happens is that, suppose this is my customer dimension and these are my attributes, right? And suppose these attributes, these, I'll mark them in different colors so that you, and suppose these attributes are these 150 attributes corresponding to the district, right? And suppose, so these are like the customers who belong to this region, right, this district. So what happens is this chunk of information, right, which I've shaded, is common, is repeated, right? So this block is repeated. So block of data is identical for all customers. So when this is the situation, we model it as an outrigger. So let us see how we do that. How to? So follow these steps for each attribute set. So create a separate outrigger dimension for each attribute set. So we're calling it dimension, but it is part of a dimension. It is not a dimension because anything we call as dimension should be directly linked to the fact table. Remove the attributes from the customer dimension. Place a foreign key to the outrigger table and no foreign key from fact row to outrigger. Outriggers attribute indirectly associated with facts via the customer dimension. This is what I explained earlier. So it looks like this. So there will be a foreign key from this dimension, customer dimension, and this is my fact table. So there is a foreign key here, there is a foreign key here, and these outriggers, so this is my outrigger and this is my dimension from where I have, so it would go like this. So let me use a different color, right? So it will go from here to here and here to here, right? So any outside inquiry would be like this. So that's what is an outrigger, and this is how you create it. So I'll show you some illustrations later. So reasons, so demographic data is available at a significantly different grain than the primary dimension, district versus individual customers. This I explained already. And data is administered and loaded at different times than the rest of the customer dimension. So that's what. So this data would be loaded at a different time than the customer data is loaded. So it is good that we have kept it in a separate table. So this would help us in loading this particular outrigger separately and more efficiently, right? Advantages: save space because you have removed a repeating block of data. Okay. And disadvantages: additional tables introduced, and accessing outrigger attributes can require an extra join, and again the same problem that we had. Users must remember which attributes are in outrigger versus the main customer dimension. And since this is a kind of a normalization, so suppose this is my customer table, customer dimension, and this is my outrigger. So what I can do is I can hide, I can join them in a view definition, right? Okay, to overcome this problem in the case of outrigger. I could not have done this in the case of mini dimensions, because mini dimensions first thing is that they don't distort the classical star schema structure of dimensional model. Here the classical structure gets distorted because you have this new kind of thing that is coming in, which is linked to a dimension table, right? So it is a kind of a distortion, and when we talk about OLAP later in the course, you will realize that many of the OLAP tools require the classical star schema to be there, right? So if there is any distortion to the classical star schema, so these tools are not able to work on such schemas, right? So that is what is the problem. So we can hide this under the view. So this takes care of two problems. One is that any kind of OLAP tool that sits on top of this, which insists on a classical star schema structure, would still be able to work. And second is that you will not be required to remember which attribute is in the outrigger table and which attribute is in the customer dimension table. So dimension outriggers are permissible, but they should be used as an exception rather than a rule. And avoid having too many outriggers in your schema, right? And if query tool insists on a classical star schema, so this you can hide the outrigger under a view declaration, which would essentially mean a join between the dimension and the outrigger. So this you can define a view. Okay, so this is about outriggers. So let me move to the next slide. So let me just summarize how these outriggers are different from. So this is a pictorial representation of the things. So you can see here on the left is the outrigger. So you can see there's a fact table which talks to the customer, which has a foreign key here, and then this here has a foreign key here. So these are foreign keys, right? And outrigger has no connection directly with the fact table. Whereas here you can see there's a foreign key here, and there's a new foreign key that I have to introduce to cater to this, to connect to this many dimension. And you can see there is no connection. So here there is a connection between the dimension table and the outrigger, direct connection. Here there is no direct connection, as you can see. So their connection is through the fact table. So this is how you can easily remember the reasons for creating outriggers and how they position themselves in the overall schema, right? So all these things can be handled. So here it does not require a view definition. Here it requires, because I can hide all this outrigger using a view. Okay. So now let me come to, once I have covered many dimensions and outriggers, so we are now in a position to talk about type 4, type 5, type 6 and type 7 changes. So this is an example of type 4. Again, the table, the figure has been taken from the Kimball's textbook that we are using, and you can see this is the fact table, right? And this is the customer dimension. Okay, so I have taken out certain dimensions, certain attributes, and put them in the customer profile mini dimension, and I've created a surrogate key, which is the customer profile surrogate key, and I have added this in the customer as part of the primary key of the fact table, right? So this is a mini dimension, and this is how we define type 4. So type 5, which is a mini dimension and type 1 outrigger. So let us see what this is. So mini dimension is type 4, right? You understand this, and I'm talking about type 1 outrigger. Type 1 is that when we try to override the changes, right? So 4 plus 1 makes it 5. Okay, so that's why the name type 5. Okay, so type 4 mini dimension with type 1 outrigger. So let me first clear this annotation so that I can make fresh ones. Okay, so you now see there is a customer table, and there is already a mini dimension that I have created. And then I also feel that there are lots of attributes which are at a different grain than the customer. So I try to create an outrigger. So here is an outrigger that I have created. What attributes go into that, don't worry about that right now. Okay, and now I have created a foreign key in the customer dimension. This is how we create an outrigger. So this is an outrigger for the customer dimension. So I have created an outrigger for this and I have a foreign key from here to here. Okay, so this is the primary key, which talks to this primary key. Okay, and on this side it is the standard story. So what this type 5 tells you is that you can have a mini dimension as well as an outrigger in the same schema, right, for the same table, for the same customer dimension table. So this is what is type 5. So both mini dimension and outrigger, actually they coexist, okay, in this. Okay, so I hope this is clear. So let me now move to type 6. Okay, type 5, there is another so what we are saying is that there is one question that comes to mind, is that why we are not implementing the outrigger as type 2 and why we are implementing as type 1. So let me take you back. I forgot to mention this point. So whenever this customer, the current profile, it changes, right? So I'll just strike off this and make it point to the new key. That's what we are doing. So that's why we call it type 1 outrigger, right? So now the question is, why are we not doing it as type 2? Because that's what we recommend all the time, that we should use type 2 and we should not overwrite any values in a data warehouse. So we would then be capturing volatile changes in the monster customer dimension, right? So if I'm just making it change every time, so here it is type 2 already, right? So any changes in a dimension are captured as type 2. So if this key keeps on changing repeatedly, so I'm again creating that problem which we set out to solve, right? So that's why we use it as a type 1. So we don't create a new record so for a customer whose customer profile key changes. So we just update it to the next to the current value. So that's the change, right? So that's why we don't use type 2, we use type 1, right? So it's the same thing, right? So current profile you can can be found out in the absence of FD matrix. So now let me come to type 6, which is the second last technique which we are going to discuss. Yeah. So it basically does what? Add type 1 dimension, type 1 attributes, right? So when I'm adding an attribute, it automatically becomes type 3, right? It is type 3. Adding an attribute is type 3, and we are adding type 1 attribute and 2 type 2 dimensions. So all 3 dimensions are involved. So combines type 1, type 2, type 3 in some way, and whatever you do with these numbers, whether you add them or you multiply them, you are going to get 6. So that's why the name 6. Okay, so I'll just explain it using this. So this is my original row in a product dimension. So this is the product key, and that is the surrogate key actually. And this is my SKU, which is the natural key. This is the product description. This is the historic department name, and initially historic and the current name would be the same, as you can see here. Row effective date, that is the date on which this record came in, and row expiration date is something like something we can never reach, and there's a current row indicator. So this I discussed, all these attributes I discussed when I was talking about type 2 changes, right? Now what happens is that this department is changed from education to strategy. Okay, so you can see here. So now you see I have introduced this as a type 2 change. So here I am implementing a type 2 change. Okay, so I'm creating a new surrogate key here. The natural key remains the same, the product description remains the same, department has changed, right? So there was okay, and the current department is now strategy, and it is effective from 1/1/2003, and it expires, you don't know when, and this is the current. And the earlier row, there are some changes made to that. So historic name is now education, and current name is now strategy. So this is a new thing that you find here. So let me use a different color so that you, where is the eraser? Not sure if that is the eraser. Let me use a color. Yeah. So you can see here, so this is the, okay, wait a minute, there is some, yeah. So you can see here, this is the change that I'm making to the original record. Current department I'm changing, and I'm changing it here because it was current earlier, so now it is expired. Okay, and here it was education, now it is strategy, and I'm creating a new record where the historic and the current are always same. So the current record would always have these two values as the same, right? Now suppose there is another change to this department, and from strategy it goes to critical thinking, CT I'm calling it, right? So now you see what happens. A new surrogate key is introduced, right? And these ones are like handled the other way. And now what I'm doing is, okay, so this new record comes, this is same, right? So what I have done to the previous records, so any changes to the previous records are not recorded, like this becomes expired, and this I'm changing in a type 1 mode, right? So all of them are getting introduced, and this current department name is the new value that we add to, new attribute that we add to the table, right? So when you need the type 2, you don't need the current department name. So this is an attribute that I'm introducing. So I've introduced an attribute which is type 3. I'm doing override, which is type 1, and I'm also introducing, maintaining type 2. So this is like type 6. Now let me come to the last so dual type 1 and type 2 dimensions. So 7 is just a number here, so there is no kind of way I can arrive at this 7 using type 1, type 2, type 3, right? So it is not, it is just the next type of change that I'm trying to explain. So is it feasible to support both the current and historic perspectives for 150 attributes in a large dimension table? So we are referring to 6. So this is basically type 6. Okay, so enter type 7 hybrid. So what we do in this is that include a natural key as a foreign key in the fact table, along with the surrogate key for type 2 tracking. And if natural key is unwieldy or ever reassigned, use a separate supernatural key instead. So what we do is that we make the natural key also as a foreign key from the fact table, right? So we introduce this natural key in the fact table, assuming that it is never going to change, and if it changes in any situation, then we introduce what is called as a supernatural key instead, right? So I'll just show it to you. So this is how it looks like. Clear this annotation. So you can see, so this is the, I'm doing, okay, wait, let me clear this as well. Okay, so you can see here the product key is added, right, which is the surrogate key here, and then there is this durable product key. Okay, so we enter this durable product key. So recommendation is that you only use the durable key, which may be the same as SKU or the natural key, or it may be different. So if you're not sure whether the natural key is, if the natural key is will change or not, so then it is always recommended that you use the durable product key, right? And then you have this durable where current row indicator is current, so everything is current. So view of the product dimension where current row indicator is equal to current. So the current department, everything is handled here. So it's a dual type 1 and type 2, right? And we basically introduce the natural key as a foreign key in fact table. So this is the situation, because, and we are trying to do this because we cannot possibly handle everything using type 6. So type 6 we introduce this new department. Now suppose the same thing happens with some other attribute in this. Okay, so how many new attributes we would introduce? So to overcome this problem, type 7 was introduced, and for this we just needed to make a change that natural key is assumed to be everlasting or never changing, and it is kind of used as a foreign key in the fact table, and if it changes due to some reason, or if it is expected to change due to some reason, then use a supernatural key in its place, right? So that's what is shown in this schema. Okay, so let me clear this. Now we have a summary of type 1 to type 7 changes. So whatever I covered, right, is there in this. So this right, so if you look at type 7, so I add type 2 dimension row with new attribute value plus view limited to current rows and or current values attribute values. So this is the type 1 part. So facts associated with attribute value in effect when fact occurred plus current values. So this is how, so this is a summary of everything. So it is important that you understand, you go through these type 1 to type 7 changes one more time. Type 0 is already also there, but that is okay. So you go through these type 1 to type 7, understand what we are doing in that, and then try to understand why we are doing that, what are the advantages of doing that, and then come to the summary table, so everything will become clear. And in the textbook there are specific examples for each situation that is given, right? So you can go through all of these, and so with this I come to the end of this topic on changing dimensions. All kinds of combinations we have covered, and now we move on to the next topic, that would be the time dimension. So we'll talk about that, and then we move on to other advanced dimensional modeling concepts like multi-value dimensions and the concept of bridge tables and helper tables, plus we talk about role-playing dimensions. So all these things would come in the next couple of lectures. Thank you.